Hello everyone. So we've gone through the Z-transform as an analysis tool for finite impulse response filters. So when we were convolving with some kind of impulse response. And then we also showed how to design some finite impulse response filters using the discrete Fourier transform. Now I want to show you a totally different class of filters that we could never analyze with the discrete Fourier transform. We have to analyze them with the Z-transform. And these are the so-called infinite impulse response or feedback filters. So to motivate this, let me show you a simple example to begin with. So I'm going to write down a difference equation for one of these filters. And I'm going to write it down as y of n is equal to x of n plus, and before we would have said something like, x of n minus 1, blah, blah, blah. But now I'm actually going to say plus y of n minus t. So what I'm going to do is take the output t samples before and add that to the input at this time. So this is called a feedback filter because we're feeding back the output from an earlier time into the output at this time. So let me actually just code this up first. So what I'll do, maybe I'll make a little bit of noise, and let me also be able to define t as 10 here. Let me make a little bit of noise. I'll seed this, and let me implement this. So I'll say, okay, y is equal to np.zeros. I'll say it's the length of x plus t minus 1. Okay, fine. Now this I'm going to have to do with a loop. So let me loop through the samples of x, or I guess I'll say length of y here. I'll say, okay, y of I plus equals x, let me use n here to be consistent with the equation. Y of n plus equals x of n plus y of n minus t. Now let me be a little bit careful here, because at the beginning, there's nothing to feed back, nothing has happened yet. So maybe I'll say if n is greater than or equal to t, then I'll say y of n plus equals y of n minus t. Okay, so that's going to do that equation. And so let's have a look at what that gives us here. Whoops, I meant to say for n in range, like the y. Okay, and I should be a little careful here. I should do a similar thing with x. I'll say, okay, I'll only actually add x if, I'll say if n is less than the length of x. Okay, so now I think I'm good. All right, so here's the signal that starts to come back here. Now, it's a little bit subtle, but if I kept going like this, so let's say maybe I do like 1,000 samples, then I see that this is starting to grow larger and larger and larger. And to figure out why that's happening, I'm going to put in, instead of random noise, a very special cosine. So let me make the omega, so in radians per sample, let me make this be 2 pi times some integer k over t. Maybe I'll start k off as being 1. And so I will make my x be cosine of, I don't know, I'll come with my n's here. Let's just say I'll start off with maybe 200 of them. Okay, so let me make this cosine of omega times n. All right, now this is very clear to see, it seems to be increasing linearly every period. And in order to see why, let's go back and think about something like the Z-transform. All right. Now this time we don't have any feed forward terms. We don't have any of these, other delays of x, but we do have a delay of y. Now if I jump down and analyze this, I can actually do a similar trick to what I did when I was deriving the Z-transform for just delays of x. So let me assume that the input is a phasor. I'll say with frequency e, I'll say e to the negative j omega, or no, I'll just say e to the j omega n. Okay. Then y of n will be a phasor of the same frequency, but possibly multiplied by an amplitude, some non-negative real number, or yeah. And then j omega n plus a phase shift, possibly. And we've been mainly focused on the amplitude shift in the examples we looked at, but we know the filter can give rise to a phase shift as well. And that'll also be true in this case, because we're only ever adding, these are all linear terms. You can never introduce a new frequency that way, turns out. Okay. So we got this. Now, let's just rearrange this equation here. And I will move this y n minus t over to the left side. And now let me look at that y n minus t. If I plug n minus t into this equation here, then I get, okay, y quantity n minus t. I'm going to plug that in for n. And now I can do something like I did before, where I'm going to factor out. So actually, I'm going to distribute this quantity n minus t through here. That's going to give me e to the j omega n. And then I'll put the phi in there. It's also going to give me e to the j, negative e to the j omega n times t. So when I factor this out, what I'll get is a e to the j omega n plus phi, just like I had before, but times e to the negative j omega t. Okay, now what I can see is this is what I told you yn was originally. So now I'm just back and looking at the same kind of thing. In fact, what I've done, we would say this is the z transform of the y terms. So I can say this is y of n times e to the negative j omega t. So yeah, the z transform, we can do it on the y's too. We were doing it on the x's before. That was for the feed forward, you would say, convolutional terms. Now we're going to do it for these feedback terms for y. And so if I plug this in, what I can do is say, all right, well, yn times 1 minus, in this case, e to the negative j omega t. So I'm just making the substitution, right? If I plug in this for y of n minus t, then I can factor out the common yn term, and I'm left with e to the negative j omega t. So I see that y of n times this is equal to xn. And now I'm in a really interesting situation, because up to this point, all of these polynomials in z, in this case z is e to the j omega t, but yeah, or e to the j omega, all these polynomials in z were in the numerator, but when I solve for y of n. But now what's going to happen is this is going to show up in the denominator. So if I solve for y now, what's going to happen is I've just got 1 on, or I've got xn on the right hand side of the equation. But in the denominator, I've got this 1 minus e to the negative j omega t. And so now it's a little bit clearer to see what might happen here. Because if I have a denominator of 0, this thing is going to blow up, right? I put in a particular xn with just the right omega, and turn the denominator 0, this whole thing is going to blow up. And so let's see, well, what omega would make this 0? What would have to happen is that omega times t would have to be equal to some integer multiple of 2 pi. So I'll say 2 pi times k. And actually, is that the only case? Yeah, because we would have to get a 1, and that's the only way to get a 1 is to be 0, 2 pi, 4 pi, or negative 2 pi, negative 4 pi, etc. And so what that tells me is that omega, if omega is equal to 2 pi k over t, then I'm in trouble. All right, so if omega equals 2 pi k over t, then I blow up. So let's check. In fact, that's what I had orchestrated here before, right? 2 pi k over t. And this is why this is growing, and it's going to grow without bound. If I keep going here, let's say I go up to 2,000 samples, it just gets bigger and bigger and bigger and bigger and bigger, and it's going to blow up. So this would be the amplitude that the thing ends up at, but actually it'll never end up at a finite amplitude. So that's why it keeps growing. Let's pick something that's not that. Let's pick something that's a different frequency. Maybe I'll just add 0.2 to this. And we'll see this one doesn't grow, right? This is not one of those ones that grows. But if let me back up just so I can see a little better here. Okay, let me do, let me go back to maybe just to 200 samples here. Okay, so that was that. What if I make k equals 2? So I make a slightly higher frequency, but one that apparently also causes problems. And that one is also growing. So somehow the issue here is that I'm adding the signal to itself in a way that it interferes constructively with itself. So it actually lines up with itself perfectly. It feeds back and lines up with itself perfectly and starts to blow up. So I want to show you another example of this with audio. So give me a second. All right, I got my headphones in now. So let's go to the audio sample right here, and let's make t be 100. So we would think, this would give rise to some kind of periodic signal that would have a period of 100 samples, which in this case is 441 hertz. So yeah, let me go ahead, and actually I'm going to set up some noise. So let's do maybe 4 seconds of noise. Actually, maybe a little, let's say 5 seconds. And okay, cool. So now I will run this code again. And let me listen. Actually, first let me plot the result. Okay, so something interesting is happening here. Oh, actually, let me do rand n. Let me do white noise instead. Okay, there we go. This is what I was looking for. Okay, so let me listen to this. You see the amplitude is growing, which is actually a little bit interesting because I put in noise. I didn't actually put in one of those special frequencies, right? So let's listen to what we hear here. So here we go. Okay. So it starts off sounding a little bit noisier. And then it's kind of closer to like almost comb filter tone emerges. Now, you probably have been in an auditorium somewhere at some point where suddenly, somebody's speaking on the microphone and all of a sudden it gets louder and louder and louder. You hear this like, ooh, tone just grow. And that's because the microphone is feeding back from the speakers that are outputting what you're saying in the microphone. And so it can be described by something like this. And there's an instability there where it's, even if you input noise, even if you're not making that particular tone, based on whatever the delay is, that tone will pop out. So if I look at like the first few samples of this, let's look at just the first 400 samples, say. It looks pretty noisy. But if I jump later, let's say I jump into 3 seconds in, now it's starting to look a lot more periodic. Okay, so what's happening is that tone that's building up is going to survive and actually grow way above the rest of the noise floor there. So hopefully now you can see why you would get that weird effect in the auditorium. So what we have here is something called a pole. This is called a pole. A pole is where you could make a 0 in the denominator here. And give me a second and I'll make a picture to show you why this is called a pole. Okay, so here's a picture I get of plugging in an arbitrary z into the magnitude of this, what we call transfer function, right? So I came up with this equation here. I'm saying y of n is equal to, really I can put it in the outside here, x of n times 1 over this. So I can study this by itself. And this would be in general, 1 minus z to the negative t. So let me write that here. That would be xn times the fraction of 1 over z to the negative t. Where I'm making z here be e to the j omega, like I was doing before, but I don't have to be limited to that. And if I, it's usually what I would think about when I'm trying to analyze these filters, because I'm thinking what they would do to sinusoids. But if I allow myself to generalize away from that and look at the entire complex plane, then it becomes clearer why I would call these special points poles. So if I make z be e to the j omega, then I'm somewhere on this unit circle that I'm depicting here, right? So this is where we'd actually care about. And what I can see here, there are points on the unit circle where this magnitude blows up to a huge value. Really infinity, although I capped it at 10 here. Okay, but if I jump back to this equation and I modify it a little bit, so instead of adding y of n minus t, I actually add alpha times y of n minus t. And I'll update that here as well. So maybe I'll say alpha is 0.9 here. Let's look at the result. And so here, I actually seem to be converging to something. If I let this go a little bit longer, you'll see that it kind of levels off at an amplitude of 10. And that's no coincidence. What happens is, so this equation is then just going to turn into everything is the same, except this is going to be 1 minus alpha e to the j omega t, and so then down here, this would be in the denominator like that. So now I can see that even if my omega is equal to 2 pi k over t, and that makes this equal to 1, I'm no longer going to go to infinity. So in this case, if alpha was 0.9, okay, this turns into 1, but that would just be 1 minus alpha. If alpha was 0.9, that would be 1 over 0.1, which is 10. So let's go down here and make that change here as well. So if I make this alpha times e to the negative t, I'll make alpha 0.9 here. What I see is, okay, it pulls these poles in a little bit, but I no longer blow up completely on the unit circle there. And actually, let me make it even smaller. Let's make it actually pretty small, 0.01. So the poles pulled in further here. And this magnitude would be, 1 over, on the unit circle would be 1 over 1 minus alpha. That would be what the magnitude is. So here it's basically just 1. But if I make alpha a little bigger, alpha equals 0.9, okay, then again that moves the poles closer to the unit circle, and they have a bigger impact. So the reason they're called poles, you think of them like a tent. They're like pulling the tent, and then the tent is going down. And you want to look at where the tent is on the unit circle, and that tells you what it's going to do to these different frequencies. Okay, so that's the basic idea. There's just one more thing I want to show you with this filter. It's kind of interesting, bringing it back to the audio. So if I were to do this again, but now use an alpha, and actually I'm gonna do something a little different at x. I'm going to make it mostly zeros, but I'm gonna make the first, let's say, just, I don't know, like 200 samples, or maybe the first t samples. I'll just make be random noise. Okay. So x from 0 to t is equal to mp.random.rand and t. Okay, and now we'll run through the same thing, except I'm going to make this y plus equals alpha. That's y minus t. Okay, so there's what we get. Let's listen to it. And actually, let me make alpha a little bit bigger. Let me make it 0.99. Okay, there we go. So this is something called Karplus-Strong. This is a model of a vibrating string. If you put just a little bit of noise and then you have this feedback, that is a model of a vibrating, of a standing wave on a string. And what happens is the wave goes up and down because you have these sinusoids that are going through, but then reflecting off of each side of where the string is tied down. But every time they bounce off of where it's tied down, they lose a little bit of energy. That's what this feedback is here. And depending on how much energy they lose, it lets it kind of die out. if they lose more energy, it dies out more quickly. But then, yeah, we get the note based on what the delay is. So if I made this delay longer, I would get a lower note. So that's an octave lower there. So there you got your simple pluck strings. Okay, now there's one more thing I want to say mathematically about this example. So if I'm looking at this equation, it's called the transfer function. What do I do to the input to get the output? If I look at this, I might realize that this is the result of an infinite geometric series. So in particular, if the absolute value of alpha is less than 1, then what we can say is, another way to write this equation is like this. It's x of n times the quantity 1 plus alpha e to the negative j omega t plus alpha squared e to the negative j 2 omega t. So we keep taking this term and then we multiply it by itself and then add it again and multiply it by itself again. This is a geometric series, but it goes on forever. And as long as the absolute value of alpha is less than 1, you can write it in this form. And so this is what shows that this is a so-called infinite impulse response. Because I could also write this, if I wanted to write it just in terms of xn, I could say, you know, I'll do the reverse of the z transform. I'll say y of n then is equal to xn plus plus alpha times xn minus t, right? Because, you know, n minus t, that would be e to the negative j omega t times xn, plus alpha squared times x of n minus 2t plus alpha cubed times x to n minus 3t, and so on and so forth. And this goes on forever. And so just to show you, so this now, it's a little bit clearer to see what the impulse response would be. So, you know, the impulse response would just be h of 0 is equal to 1, h of 1 is equal to alpha, or sorry, h of t is equal to alpha, h of 2t is equal to alpha cubed, or sorry, alpha squared, h of 3t is equal to alpha cubed, etc. So now this is how you'd write the impulse response. And just to show you that I'm not lying, let me actually compute the impulse response. I made a little helper method up here to do this apply one light filter thing. So if I were to make just an impulse, if I said x equal to np dot 0 is, let's say 100, or let's say maybe go a little longer, 200, I'll say t is equal to 10 for this example, and I'll make alpha be 0.9. Let's have a look at what we would get. So if I apply one lag filter, x t alpha, oh, I forgot to actually put the little impulse at the beginning. So I'll say x0 equals 1. So just a little impulse right at the beginning. And this is what it looks like. So this is going to be every 10 samples I'm going to multiply by alpha. So I'm going to feed back, and every time I decay by an amount of alpha. So yeah, that's just to show you that this trick with the Z transform. You can go back the other way from a geometric series, the result of an infinite geometric series, and see that this is an infinite impulse response. That's what happens when we feed back. We have a chance to keep going. So that's probably enough for this video. I'm going to make another video where I follow up on this and go with more feedback terms and show you how to use this to design filters. But this was a lot just for this one example. And I think if you get this example, you'll be able to get it all. So let me pause there for a moment and let that sink in.